Hi, everyone. Hey, my name is Robert Dura. I'm an engineer on the JAX team, and today I wanted to give you a presentation on an intro to JAX and TPUs. Before we start, take a look at the RSVP link because this presentation will end with a Q&A. So ask your questions there, and I'll be happy to answer them. So we'll do the presentation first, and then the questions. All questions welcome. Okay, so let's jump into it. I want to talk about three things today. I want to introduce JAX to you. So this is going to be like a quick intro to JAX. But then I also want to talk about TPUs, which are the computational chips from Google that are super useful for ML and computational or scientific computation in general. And then finally, I also want to talk to you about a bit of a more advanced topic, which is the Palace, which is a JAX kernel language that really ties the two things together. So it lets you use the full power of the TPU from directly from a kernel language from JAX. So we'll just go over these sections, or these three sections, and let's start with JAX. So if you're not familiar, JAX is essentially a language for scientific computing. It's extremely useful for general scientific computing, but especially machine learning. So JAX really is designed to be very close to math. So if you're, when you're working with computation, when you're doing research, the point is to let you express math as easily as possible, and then translate that directly for you on code that runs on the accelerators, runs on CPU, GPU, TPU. So the first cool thing about JAX is that it re-implements the NumPy API. So if you're familiar with NumPy, this is the really cool language for array programming. Typically, if you already have a NumPy program, it's often as easy as just importing NumPy from JAX. And what you just did is you created your first JAX program. So JAX implements a lot of these NumPy operations. And if you just change your import, that's it. You now have a JAX program. What's cool about this is that while NumPy runs on the CPU, a JAX program runs on basically any accelerator device. So think of a GPU, TPU, but CPU also. So you can write a program, you can test it locally, you can test it on your laptop, and without any changes, you can deploy it directly on the GPU or TPU. The point of JAX is to let you stay close to the research, the math, and really so that you don't have to make too many changes, often no changes at all, and have your code run really efficiently and really fast on modern accelerators, modern chips. So let's take a look at the program here on the right. So what I'm doing here is I'm essentially doing a very simple neural network. So I have a list of parameters that you pass through, you produce outputs of this simple neural network, and then we have a loss function that we just compose. So when you create a function, it's just like a Python function that computes something, you can compose it with another, and as long as you use these JAX functions, instead of NumPy functions, JAX functions, your program just works. The cool addition that JAX does that is not present in NumPy is that JAX has a lot of really useful transformations. So transformations are just essentially a way of converting one function into another. And probably the most useful of those is automatic differentiation. So if you're doing any kind of optimization, if you're doing machine learning, if you're training your model, here on the right, we have an example of a simple neural network. So we want to train it. We want to be able to get gradients. The grad transformation is something that now takes as an input, not your data, but actually the function itself. So this is where the JAX magic really lies. You've just expressed your initial program that computes the loss in JAX, and now you can transform that JAX program using a JAX transformation and get the derivatives automatically. So there's really no need for you to do anything. You just automatically got a program that computes the derivative with respect to parameters instead of the loss function. So here is another really cool transformation. Oftentimes when you write code, you want it to work on many examples. If you have a data set, you want to go over that data set and compute operations per example. It's often a little awkward if you want to write your code in such a way that is already amenable to putting sets of examples in, it's often easy to just express the mathematical function you have, maybe your custom loss function or some other form of numerical research you're doing, and then just simply use the JAX transformation to get a batched version of this. So here what we're doing is we wrote the loss function as if the batch is just a single example. So we didn't have to add a batch dimension ourselves. This is just the power of JAX transformations. So this is useful. You can still use array programming, but really this is to show you just how powerful JAX is and how you can take your initial functions, apply a set of transformations to them, and get a much more powerful program. The batching function here, for instance, takes the in-axis argument, which lets you specify which axes to leave alone. So your parameters in neural network should be shared across all examples, and which axes to batch. So the examples are batched along the first axis. Another super useful transformation in JAX is compilation. So JIT, just-in-time compilation, is something you can add to your programs. And this is where we really start bridging the gap between the code, the math, and how the code can actually start running on accelerators. Now, every single one of these functions in NumPy that JAX implements can directly run alone, but you can also now take your whole program and compile it directly to run on the accelerator or your CPU as well, really efficiently. So this is another transformation. So we apply it to the output function. So here we just take our gradient function and we surround it with JIT that you just imported from JAX. And JIT is really useful. It can fuse functions together. It can eliminate repeated and dead code. So you don't have to really worry about optimizing your program. JIT can do this for you. Really, all you have to do a lot of the time is just annotate your function with JIT. But finally, I think in the modern day and age, when you scale your workloads and when you compute machine learning workloads on many chips at a time, it's super useful to be able to parallelize your computation across many devices. So I don't necessarily want to use just one GPU or TPU. Maybe I want to use 10 or 16 or 100. JIT, when you wrap a JAX function with JIT, can automatically do this for you. Oftentimes, it's really unnecessary to make any changes to your program. All you have to do is you add JIT, and suddenly your data, your neural network can run across many devices at the same time. Sometimes, if you want additional control, you can add additional sharding constraints. So JIT should work very well out of the box, but it also gives you a way to control how your program is distributed. So we're actually going to be talking a lot about this later in the context of TPUs and the context of more advanced JAX usage. But parallelization is extremely native to JAX, and it happens directly in this core transformation JIT. So yeah, this is the quick intro to JAX. And now I wanted to show you essentially how JAX works. So what are the steps to sort of demystify JAX and show you exactly what is happening? So when you write JAX, you write this NumPy program. You write using NumPy operations. You program on arrays. And so you create a Python function, or maybe several Python functions. The first thing that JAX actually does is it's able to trace your computation. So it goes through the operation, through your computation operation by operation, and creates this intermediate representation. So this is JAXPer. It's a representation of a JAX program. There are many ways to convert code, high-level code, into a representation that can be easily adjustable. But JAX uses tracing, which is really powerful because it lets you make use of really advanced metaprogramming directly in Python. You can create functions that compose other functions, and then you can directly use JAX and the JAX transformations on top of those. So once you have a JAX program, you can actually do quite a lot to it. You can take its derivative, you can batch it, and so on, like we discussed a couple slides earlier. Now, once you've done this, the JIT transformation is able to convert your program, your NumPy program, into this high-level representation of your computation graph. So you're performing some computation. JAX first creates this representation of a program, and then you can transform it, but finally you convert it into this high-level representation of operations. And the real power of JAX is how it interacts with the XLA compiler. So XLA is a compiler. It's a compiler that can target so many different accelerators. And this is also what gives JAX the ability to run on so many accelerators. So once the JAX program is converted in the high-level representation and you pass it to the compiler, you really unlock the ability to run the same code in Python that you wrote on any accelerator. And it's not just the type of accelerator, CPU, GPU, TPU. It's also whether it's just a single chip or 10,000. And this really is JAX's core focus. So the point here really is to do two things. To both be agnostic to hardware, so that you can run your experiments on your laptop. You can start with simple programs. You can quickly develop your machine learning code or your scientific computation code, and then deploy it on any accelerator with essentially minimal code changes. Typically, when you write a JAX program, a change that would be necessary is how you want to parallelize it if you don't want to use the automatic way. But you don't have to specify which accelerator it is. And finally, JAX also introduces this array representation. So when you start learning NumPy, you start learning array programming. So you start working with arrays instead of individual floating point numbers or individual scalars. JAX pushes this concept further. So instead of just talking about arrays, JAX has this concept of a sharded array. And so the point is that in modern workloads, in modern machine learning workloads, but also large-scale workloads that people have been running for years, for decades really, it's often insufficient to just use a single device. You really want to make use of a lot of different devices. So say I bring two devices here, and I have some computation. What JAX does is JAX introduces the concept of a sharded array, and a sharded array is an array where the chunks of this array live on separate devices. So I can have half of my array live on one device and the other half on the other device. And once I've done this, the JIT transformation is able to parallelize the computation. So it's not just that the data or the parameters of my neural network live on two separate devices, it's that once I start computing with them, JAX distributes this computation for me. So it really focuses on being able to scale really easily, scaling via this single global representation of a sharded array. So you take your initial computation, you combine it with several devices, and suddenly you have a sharded computation. And that's really powerful because it really lets you write high-level code, but train extremely large machine learning models or accelerate your computation that would normally take hours on a single device to now take seconds if you use many, many different devices together. So what we just discussed, what I was just essentially showing you, is that JAX starts at this high level of flexibility. So you can directly compose NumPy operations, and you can even add JIT to them to compile them and make use of automatic code optimization. And you can add, and the very same transformation JIT also lets you parallelize across many devices. So what happens is that we essentially just discussed the first two dots on the flexibility versus direct control curve. But JAX is a research framework, so it really lets you do computational and machine learning research really well. So it also gives you the ability to go a couple steps lower, which is usually a little harder to express, but gives you much, much more direct control. So we like to draw this curve to essentially show that you're trading off a little bit of flexibility for much more direct control. The three really cool dots that you can going to the right is first this shard map, which I'm going to talk about in just the next slide, which is how you take direct control of how devices communicate, because before JAX was doing this for you. Then there's an even lower level, which is the kernel languages. So you directly write in a way that the hardware understands on a very low level. But JAX also gives you the ability to call external code. So if you're a GPU researcher and you're writing CUDA code, JAX has a direct module to be able to let you call your CUDA code directly from JAX. So you don't have to decide between CUDA or JAX. You can use both at the same time. But let's focus on the shard map now, because I think this is a lower level approach to writing JAX programs, but one that is extremely useful for machine learning research and scientific computing. So shard map, before I was telling you about these sharded arrays, which is how JAX represent these global arrays that have multiple chunks. But now we actually want to drop to the per device view. So if I'm computing on 4 chips and I want to communicate between them directly, I want to at some point be able to have the control over what an individual chip does. And then I want to tell the chips directly how to communicate, when to do computation, when to do communication, and retain that control. So I'm going to talk over this example on the right, which I think is really cool. And this is a distributed matrix multiplication. But I wanted to say that the composability of the JAX transform is so powerful that even though you're now going a level lower in terms of control that you're retaining of your program, but you still remain composable with the previous transformations. So the program on the right that you're seeing deals with communication directly, but it's still automatically differentiable. It can still be automatically batched if you want to. So JAX really, I just really want to show how cool it is, how strongly JAX supports this composability. But now getting back to the shard map, the stuff that lets you express the per device view and talk about the communication between chips directly. So what you'll do is you'll start with these inputs to the function A and B, but once you actually drop into the shard map function, you end up with the not the full array, but instead the chunk of the array that lives on a particular device. And if I want to do a distributed matrix multiplication, I will first multiply these shards together, and I will then explicitly tell the chip to communicate. Now, what happens here is I would then first do the computation and communication, and then return the result that is reduced on all the chips. I hope you can see that this is just a starting example, but a simple, really cool extension would be to overlap computation and communication. So you could directly use JAX to write your own method that performs this matrix multiplication much faster, where you can multiply in chunks, you can exchange those chunks at the same time as you're computing the future result. Shard map is also super useful because it's a direct connection with the type of parallelism that is super popular and really useful for a lot of workloads, which is the MPI style communication. So in that case, what shard map gives you access to are these direct communication, like all reduce to reduce the result over all the chips, all gather to collect chunks from all the chips onto every single chip, all to all, exchanging messages, and permute, which directly lets you send messages between devices. This is cool. In, say, machine learning research, it's super useful. Shard map is super useful for mixture of experts model. If you're familiar with the DeepSeek paper, they talk a lot about how they exchange messages, the token messages between devices that contain only a subset of experts, and this lets them perform really powerful expert parallelism. And shard map is essentially a perfect tool for this. It also lets you do research on custom style communication. It lets you hopefully perform this scientific distributed computing in a way or style that best fits your needs. So on one hand, you can use the global sharded array view, but you can also drop into shard map if that better suits your needs, which all goes back to the story of flexibility that JAX gives you. Whatever is fastest for your research, that's what's available directly to you in JAX. Moving on from the shard map, JAX is the core computational library, but it also has a whole really cool scientific ecosystem available. So the JAX really stresses that composability, which is something I was talking about before, which is that transformations are composable. And that means that when people build scientific packages for the ecosystem, these retain high level of compatibility. So you can take one package, combine it with another, combine it with a third package, and they will all work together. I wanted to highlight some really cool packages. We have an NNX library, which is a library for expressing neural networks in JAX. There's Optax, which is an optimization library that lets you both use existing optimizer. If you want to, say, train your neural network with AdamW, the AdamW definition is directly available in Optax. But you can also write your own custom optimizers. Optax is used by a lot of researchers to work on custom optimization research. There's also Grain for a really cool sharded data loading. So when you have a lot of different devices and they all need to process huge data sets, you can split that data loading between devices, and Grain lets you do this directly in JAX. There's other recent libraries that we have. We have Quix for quantization. We have Tunix for fine-tuning your models. So definitely check out the ecosystem. I wanted to show you our website, which is just jax.dev. And I think it's not just documentation. Really, jax.dev, the website that we maintain there, is a combination of three things. It is the intro to the language, so definitely you can read on how to get started with JAX. It is also an API reference, so if you're already much more familiar with NumPy, with scientific computation, you can look up how to use specific functions or the API for them. But what I found super cool about the website is that it also has a lot of both intro and advanced computation guides. So these are guides about computational concepts that are really presented in a very general way, and then also implemented with JAX examples. So if you want to learn about computational stuff, the JAX docs are a really cool resource. Definitely take a look. So now, after JAX, I wanted to talk about the second part of this presentation, which is where I wanted to show you TPUs, both what they are, what the history behind TPUs are, but also really how to practically program them. Because I think TPUs are one of those chips that are just that lends themselves really well to programming. But before I do this, I also wanted to shout out again the RSVP page. If you have any questions, we're not going to interrupt now, but at the end of this, we'll have a Q&A so that I'll be able to answer your questions then. Okay, let's talk about TPUs. And I think TPUs are best presented by enumerating their strengths. So the really cool three strengths of TPUs are, one, that they can perform really fast computation. So they really focus on making sure that when you throw data at them, they can compute it extremely fast. That's one of their focus. The second focus is that they include very scalable chip networking. So when you get TPUs, it's usually not just a single TPU, but it's groups of them. And the communication between them, like say we're talking about SHARMAP, like you can communicate between chips, the communication hardware is actually extremely well designed for TPUs. And finally, the third strength of the TPUs that I think is underappreciated is that it's a very uncomplicated architecture. And that means that when you're, as a researcher, as a programmer, are using those, you can really dive low level, but still write programs that are easy to reason about. So it's both low level control that is easy, thanks to just the genius simplicity of the design. So TPUs are accelerator chips. They're used to accelerate machine learning workloads and any computational workloads, really. Google has a long history of creating these computational accelerators. It dates all the way back to the release of TPU v1 in 2015. It was released for internal needs. And then there's a series of TPU generations that kept improving upon one another. TPU v2, that was the first publicly available one, all the way until now. And I'm going to show you the latest generation, the 7th generation Ironwood, that is being released this year. The latest chip is really extremely fast, and it's designed for really the modern machine learning workloads. It's really good. I wanted to show you what a TPU consists of in terms of what it does. So let's take a look at Trillium. This is the 6th generation TPU. And so the important stats here is that it's an extremely fast matrix multiplication unit. So if you take a look here, you can perform computation in bfloat16 and in int8. And these are extremely high numbers. So this goes back to the first strength of the TPUs, which is the really fast compute. But what's also important is that they have a lot of very fast memory. So on each chip, the chip will have this high bandwidth memory. And it's a really useful feature because, say, when you're serving neural networks, when you're serving, say, LLMs, that memory is really working very hard. The chips have also the really good communication. That's their second strength. And What that means is that they are both very fast, and the 4 means here that they're connected to 4 neighbors. So I'll talk about how TPUs are connected, but what's cool to see here is that that's a very important aspect to them. It's not just that an individual chip computes, it's also how they communicate and they connect together. And what we also have done is that we have a limit on the pod, which is the sort of group of TPUs that are very efficiently connected. You can go beyond that. I'll talk about this a little later too, but this is also their topology and how they're connected. Finally, TPUs consist of this main computational chip, but they also have some specialized hardware too for some alternative workloads, like gathering tokens for, say, recommender systems. So the device itself, you can see a picture here on the right, is years of experience of Google designing these. Now, what I showed you was the previous generation TPU. What we now have available is the 7th generation. It's called Ironwood. It's becoming available now, and it's extremely, extremely powerful. It made two very cool leaps. It's both computationally much faster, but also the scaling strategy is such that now you can connect so many of these chips together that workloads that really require a lot of compute, that require a lot of scaling, are much easier done on the Ironwood chip. So I talked about these 3 strengths. I wanted to dive deeper into them. So let's start with the super fast compute. Essentially, first, how a TPU works. So hopefully you can see this on the slide in the top left. A TPU consists of 3 units, really. It's a high bandwidth memory connected to these 3 units. We have a matrix multiplication unit, which is responsible for multiplying matrices. We have a vector operation unit. So this is for all types of array operations that are not matrix multiplications. And finally, we have a scalar unit. That's the unit that's most used for conditional flow, when the TPU needs to decide which memory to load, or what to compute. And the reason why I mention this is because the reason why I'm talking about these details is that is essentially it. When it comes to understanding this TPU chip, if you can understand that it's just really, really focused on these 3 things and doing them really well, and we'll see later in the later section of this presentation that this is the mental model here is all you need to program these chips on a very low level and get really 100% performance out of them. So probably the most important part of this chip is the matrix multiplication unit. So let's talk about how the matrix multiplication unit works on the TPU, because it's really cool from a hardware perspective. It's the biggest unit on the TPU. It's responsible for computing matrices, and it uses something called the systolic array. So in order to compute a lot of matrices, a lot of numbers, a lot of flops at the same time, instead of doing this one by one in maybe a hardware loop, what it does instead is it has this grid of sliding data. So it's streaming a matrix multiplication by feeding the left-hand side of the matrix multiplication, the right-hand side, and popping out the output. And this circuit is extremely efficient because it works on all this data at the same time. You start sliding your input, and the circuit computes all these numbers at the same time. And this is really crucial. This is the key to the design of how these TPUs can be so extremely fast. Second strength of the TPU is the interchip networking. So this is just really for going beyond a single chip. And what's really important here is that the topology that these TPUs are connected in is fairly simple. So you can see in the drawing in the middle that when you take a TPU, what you do is you connect it to 4 neighbors. So it's the chip to the left, to the right, up, and below. And they also have these additional connections that go around. We call them the wraparound connection. And that really makes it so that the communication in this network of TPUs can be done extremely efficiently. These links are both really, really fast, but this simple topology, here, this is an example of a 2D topology because they're laid out in a 2D grid, but we also have 3D topologies where they form a cube. And then each TPU chip has 6 neighbors. These pods have a certain size. So at some point in some generation of TPU, we, I think, had a pod size of 256 chips. If you want to scale your workloads beyond that and for really the largest neural networks, people do that. You would connect the other chips with data center networking. Google has decades of experience in data center design, and so if you really want to go beyond these pods, it's also possible. You can connect multiple pods and connect them via network like that. What the networking results in is that when people scale the machine learning workloads to more and more TPUs, in order essentially to cut down on the training time of a large network, or if you have a fixed time budget to be able to push more data in your training process, what they discover is that these TPUs exhibit really near optimal scaling. So if I add twice as many TPU, I get twice as fast computation. My training time goes down by exactly half. Which is an extremely cool result and really validates this genius design of the networking in the TPUs. The Ironwood, the latest generation of TPU, has these pods where previously I said that some of these pods at some generation were 256. Now these pods go up to 9,000 TPUs. And that includes, in total, almost 2 petabytes of shared memory. But if you want, you can even scale beyond that. So it's still possible to connect these huge iron pods together via data center networking. Practically, when you provision a TPU, you can provision a whole pod. The Ironwood is 9,000 chips, but you can also actually, these TPUs are connected to host machines because you drive them via regular CPU. I think we use server-grade Linux. They include really fast CPU there for, say, data loading, a lot of RAM, really efficient network storage. And if you want, you can really ask for any number of TPUs. And what happens is the TPU sits in pods, but you can ask for a subslice of these TPUs. So here on the figure on the right, if I want to compute with 4 TPUs, I would just request 4, 8, or 16. And this is very easy. You don't have to provision the whole pod. Practically, you can scale really easily to any number. The final strength of the TPU is its uncomplicated design. So we talked about how it consists of these 3 units: matrix multiplication, vector unit, and scalar unit, connected to a memory. And we're going to talk about this actually in a second, because I want to tell you about how to program these TPUs on a very low level with Palace. But so I wanted to introduce how a TPU computes an operation. And the design directly follows what's on the right. So if you see how a TPU is structured with this memory and these three types of operators, it's just that whenever you want to perform any computation, you'd start with the data living in your accelerated memory, the HBM. You then move that data to vector memory, the memory that's really fast but much smaller. And then from that, you would compute using either vector or matrix multiplications. And this also might seem like a detail, but it really is that simple. And it'll really let you program these TPUs on a low level with Palace quite easily. But to recap, the TPUs, I think, are quite easy to understand via these the 3 strengths, the 3 focuses that they have: the super fast compute, the uncomplicated architecture, and the really scalable chip networking. But next, actually, let's see how to program them, because I promise that this is going to be more of a practical guide too. So let's take a look at programming TPUs. On a high level, it's really not that complicated. You can write a JAX program. The JAX program, as we discussed, compiles to a high-level representation that then passes through the XLA compiler that directly generates code that runs on the TPU. So that is essentially it. In JAX, you express parallelism, so you use shard map in JAX, or you just rely on sharded arrays in JAX to distribute computation and communication. Then this program gets represented as HLO, and that gets compiled. Now, I want to tell you that it's not just JAX. If you're a fan of PyTorch, you really can make use of the XLA compiler to represent the computation in any framework of your choice that's compatible with XLA, and PyTorch is. So you can write your program, you can put it in the XLA compiler, and at that point, the XLA compiler, it's so compatible that it can lower your program, it can compile your program to any number of backends. So a CPU, GPU, TPU. This is quite useful actually in practice, as I was saying before, is that you really don't have to program directly on the TPU. You can experiment locally on your laptop directly on your CPU, and you can then deploy this program with minimal changes on a large-scale cluster, which I think is extremely cool, and it's a very, very cool aspect of the XLA compiler. When it comes to how an actual TPU program might look, I wanted to show you a time trace of one. So what you're seeing here is essentially a timeline of the operations that the TPU is executing. These blocks are roughly on the order of tens of microseconds. But this whole stack from JAX through the compiler down to the device is really designed to be extremely fast. So what you're seeing here is, this is, I think, the program of my implementation of DeepSeek R1, and this is DeepSeek R1 decoding a batch of tokens. So what you do is you start with the JAX program, you apply JIT to it, and you deploy it on the TPU. And also the profiling is really mature, so you can directly take a look at what's happening. This is really the point is to give you as much insight as you do research as possible, because the faster you can move, the more research you can focus on. Now, I wanted to conclude briefly about TPUs themselves and now move on to the Pallas kernel language. So JAX really is powerful in representing these high-level programs, computing or creating programs really quickly, iterating really quickly, using NumPy operations, using sharding. But really, if you want to use your device to 100%, or if you want to use a very particular structure in your problem that you're working on, a kernel language is a way to express this very low-level code and make the accelerator run really fast for you. So Pallas is essentially an alternative to programming TPUs, which is, instead of what we were doing before, which was creating a JAX program, going to a high-level representation, and then using the compiler to compile it to the TPU code. What we now can do is we can write a Pallas kernel, which is going to be much more low-level, and it'll go essentially through a TPU assembly, through the compiler, and be able to drive the TPU directly like that. So it's an alternative to JAX, but they're also very compatible with each other. So the most common applications that you would write your program, and if part of it or the core computation needs to be faster, you can rewrite that in Pallas. Or if your core computation is not easily expressible in terms of existing operators, although JAX is quite flexible, you can write that in Pallas. Pallas is also runnable, as you can see on this figure, directly from PyTorch. So when you write a Pallas kernel on the TPU, you can also call it from PyTorch. It doesn't have to be JAX. So let's go back to the figure of flexibility versus control. And now let's specifically look at the case of TPUs. So we're not just in this general land of any accelerator, but specifically TPUs. And there's going to be a small change. Pallas here is an excellent choice. This is the one step lower below ShardMap that we discussed earlier. But Pallas is also on TPU everything you need to program them. Writing any lower level code is really unnecessary. With Pallas, with this kernel language which sits in terms of complexity somewhere between a high-level JAX program and a low-level language like CUDA, is really everything you need to drive a TPU, to use a TPU at 100%. That really stems from the third strength of the TPU, which is just how geniusly uncomplicated the design is. So again, Pallas is useful. When is it useful? It's most useful when you want more direct level control. So if you want to use the hardware directly, if you want to use specific features of the TPU, you would really Pallas comes in extremely useful. If your problem has a specific sparsity, specific structure sparsity, Pallas is also very useful. The attention operator that's so popular in transformers sometimes is computed with a very structured, very weird, very bespoke sparsity. Pallas can write this low-level code that really exploits this. That you get so much control that you can write low-level loops, you can perform custom communication. It lends itself really well to a lot of the applications. In, say, research on mixture of experts models, the number of tokens that get routed to each expert can vary a lot and vary on runtime data, based on runtime data. Palace is extremely useful for stuff like this because you don't have to stick to high-level array programming. You can go really low-level. Palace is really a kernel language. So say if you're familiar with something like Triton on GPUs, Palace is a bit like this. It tries to give you both low-level control, but also stay fairly quick in writing so that you don't have to write a lot of code. You can write concise code, but that code with direct control. The difference between Palace and Triton is that Palace really focuses on explicit control over the memory pipeline. So we're going to talk about this in just 1 second, but essentially that figure I showed you earlier, where you control what goes from memory to the fast small memory and what gets computed there, this is Palace's bread and butter. This is where really the focus lies. And because it's a little more low level and gives you this explicit control, it can really be much faster. It can really achieve state-of-the-art performance. So Palace is definitely lower level. Palace includes several dialects. So there is Palace available for GPU. There's a Palace GPU dialect. We're going to be mostly talking about the Palace TPU dialect for TPUs. These programs are often similar, but not quite the same. At this level of control, it's often necessary to write these things slightly differently, which is the trade-off curve, essentially. For instance, Palace does not include automatic differentiation. So in that sense, it's separate to JAX, that you cannot apply automatic differentiation to it. But Palace can be used to write the forwards and the backwards pass through a routine. So if you've read the flash attention paper, they describe how to write the forward pass. They describe how to write the backwards pass. Both can be very, very well expressed in Palace. This is essentially the cost of the low-level control that Palace gives you. But let's go back to the picture of the memory pipeline and how the TPU works, which is you pull data from the HBM, you put it in this fast VMem memory, vector memory, and then in that vector memory, you directly compute using either the vector unit or the matrix multiplication unit. So let's take a look at a simple kernel. This is an addition kernel. So we just want to add two numbers and write them out to the output. You can still use this NumPy-like structure. A lot of NumPy calls actually directly work in JAX. You can multiply, you can call a multiplication. Here, what we're doing is we're reading the data from the references into X and Y. We're adding them together, and we're writing into a variable called out. And then we're storing that out variable in the output reference. In order to write this kernel, though, you also have to be able to call it. And this is where this extra level of control that Palace gives you enters. It's not just the kernel, it's also the memory pipeline that you're specifying here. So what happens is you have to write how and in what order these chunks of memory should go from the high bandwidth memory into the fast VMem. So this block spec is a way to express this. And this is really the close connection between Palace and TPUs. The way you write a Palace kernel is exactly how TPUs actually work in practice. Let's move on to a little more interesting kernel. And I want to show you this change, which I think is very interesting. So we're interested in writing a matrix multiplication kernel that uses 100% of the chip. So we really want to be able to, not leave any performance on the table. And if you see on the right, the kernel, the actual body that performs computation, is just a single line. So on the top, where I'm defining the manual kernel, it's just multiplying two tiles. So this is the memory pipeline in the abstract. The specific memory pipeline for matrix multiplication looks something like this. And what you're doing is you're essentially taking these blocks, multiplying them together in smaller blocks, and then after you're done with a row and a column, you're able to store it back. Now, what's really cool about TPUs is that unlike GPUs, TPUs usually compute with a single core sequentially. So the chip is actually able to go through these blocks one by one. It's literally one after another. and write it back to the memory and perform extremely fast. If you look up the statistics for these chips, they're extremely fast. But this all happens in this pipeline. This is simple pipeline that you specify here. What's cool is I don't have a code demo in this presentation, but I could show you that a kernel like this, so a single line of a kernel and about, say, 20 lines of Python code for specifying the memory pipeline, is actually able to achieve 100% of the TPU utilization. So I can really match the headline statistics with just this code if I want to multiply two matrices. I think that's a really cool result. So slightly more advanced, this Palace gives you, as I said before, control over the entire TPU. So it's not just the computation, but it's also the communication. If you are familiar with this type of communication, this is the remote direct memory access. And so in Palace, you are able to essentially directly write which chunks of data you want to transfer to a neighbor TPU. Because again, TPUs are not just really fast chips, they're also really well connected together. So the networking is really good. So here's an example of how I would send direct chunks of memory from one chip to another. And what's cool here is I don't need to have a structure. I can write from the first chip to the second. I can write between the third and the fourth chip, and I can all express this in this Palace kernel code on the right. Now it's not just a single line now, like the matrix multiplication kernel, but it's also quite concise. So these copies that I'm doing right now are just Python. This is a Python kernel language that you can use this. I have a link here below to a full guide. So this is what I wanted to tell you about earlier, which is the JAX.dev website includes a bunch of really cool guides. So this guide talks about how to perform distributed communication on TPUs with Palace directly. As an example of what would be a useful application for this communication is an all-gather kernel. So for all-gather, you have chunks on each individual device. So device 0 contains only the 0th chunk, device 1 only the first chunk, and so on. And what you want to do is you want to make sure that all devices contain the same chunks. This is super useful because this pattern is essentially exactly how you do FSDP. So if you're training a neural network with FSDP, this is an operation that you're going to have to perform over and over and over. So on Palace, like I was saying, the TPUs are connected in these cubes, either 2D or 3D. In this case, we have two example 3D topologies. And each chip is connected with its neighbors. So the way you'd write this in Palace is I would write these chunks to the neighbor, and then I would keep passing the chunks through my neighbors. A cool result, actually, is that if you have an n TPUs, the side of that grid will be the cube root of n. And so the number of actual communications that you have to perform an all-gather is a cube of n. So despite the fact that you scale your chips to a large number, the time it takes to communicate data between all of them is the cube root of that. So to recap, Palace, JAX, Palace, and TPUs, I think come together conceptually on this figure. The devices are super powerful. You can program them with JAX on the high level, with NumPy, with JIT. You can add sharding constraints. You can add some sharding hints, or you can do it directly manually with shardmap. And you can use Palace directly on TPUs. And on TPUs, again, Palace is super powerful. So this Python level code that you're writing, the memory pipeline, the kernel itself, is enough to get 100% out of these TPUs, which makes, I think, numerical research really fast, and it lets us move really fast with new applications in machine learning and scientific computing. I wanted to show you some resources before we go to Q&A. Again, JAX.dev is a super cool guide both to JAX itself, but also as to computational concepts. We also have a JAX AI stack, and this is a way where you can explore the JAX scientific ecosystem. So you can explore the libraries for neural network construction, for training, for optimization. If you're interested in scaling, in computational scaling, say how to train a large LLM, we have a scaling book, which isn't JAX specific, and instead talks about just general scaling concepts in compute. I think it's a really cool guide. It consists of several chapters. Um, but yeah, we talked about JAX, we talked about TPUs and how they're useful for compute and what their strengths really are. And I showed you some of Palace, which I think is really how you can unlock the full potential of these chips. All right, thanks so much for watching. Really appreciate it.